or with the venture capitalists, even though I think it's the most honest case. Okay, so in theoretical computer science, we sort of we like to organize problems into these classes and give them these weird sequences of capital letters. Physicists are much better than us at naming things. They call them, quark, black hole, right? We're stuck with non-deterministic polynomial time. Okay, but this is sort of our world map where the real holy grail of computer science has for 60 years has been what are called these NP-complete problems. So just to explain what this means, P stands for polynomial time. It's the class of all the problems where there is an algorithm running on a conventional computer, like the one in your pocket, let's say, that uses a number of steps that grows at most like the number of bits in the input raised to some power. So like a linear time algorithm, a quadratic time algorithm, O of n squared. Okay, and most of what we do with our computers on a day-to-day basis involves solving problems in P. NP stands for, as I said, non-deterministic polynomial. It's all the problems where if someone gave you the answer, then there's a fast algorithm for checking it. Okay, but it might take exponential time to find that answer. So factoring, very famously, is an NP problem. Okay, because however hard it is to find the prime factors of a giant number, if someone hands them to you, it's pretty easy, at least for your computer, to multiply them and to check that they are correct. The NP-complete problems are, in some sense, the hardest problems in NP. Okay, they're the NP problems that if you could solve those, then you could solve every other NP problem. Okay, the huge discovery in the 1970s that really started theoretical computer science as we know it today is that tons of the problems that we really want to solve in practice, the famous traveling salesman problem, sort of bin packing, all sorts of optimization and scheduling problems, they're all NP complete. Okay, and now quantum computing comes along, and it sort of it does something to this picture. Okay, so this is BQP, bounded error quantum polynomial time. I drew it with this wavy border because everything quantum is spooky and weird, right? BQP contains classical P, so anything that a classical computer can do, a quantum computer can do as well. Okay, for most of it, you wouldn't want a quantum computer, right? Like people say, well, will we use quantum computers, for playing video games or for sending email, or when will I have one on my desk to do those things? And like I say to them, well, it's like, would you use the space shuttle to taxi people around a parking lot, right? It's like, it's not that you couldn't, it's just that there's not a point, right? What we really care about is, is there anything in BQP that is not in P, right? And what Shor's great discovery was that this factoring problem is in BQP, okay? Which means that either BQP is really bigger than P, or else factoring has to be in P, right? Or else there is a fast classical factoring algorithm as well, something that no one has ruled out. In the other direction, we don't know whether BQP is contained in NP, which means there could be problems that a quantum computer can solve where a classical computer cannot even check the answer in a reasonable amount of time, let alone finding it. Okay, that will be a very relevant point for us later. Okay, now, as far as anyone could prove, right, we can't even formally rule out the possibility that all of these things and more collapse down to P, right? So, the greatest unsolved problem in theoretical computer science, maybe the greatest in all of mathematics, is called the P versus NP problem, right? Just to prove that NP is larger than P. So we can't do that, and so certainly we can't prove today that BQP is larger than P. We can't do it, but as quantum computing people, it's not our fault. Okay, it's just that mathematics has not advanced to the stage of being able to like prove these classes are different. The most we can do is to say like, well, either they're different or else factoring is in P, stuff like that. Okay, so that's just a little picture of how this fits into theoretical computer science, how quantum computing fits into it, as we've understood it since the 1970s. So let's come back to this question of, what else could a quantum computer be good for? And, as I said, there's been a lot of excitement about, well, maybe we could get more than the Grover speedup for optimization problems or machine learning problems. Maybe, even if we can't prove it, maybe in practice, we'll have heuristic quantum algorithms, and they'll get these speed ups for reasons that no one really understands. Okay, just like modern AI, is changing the world, even though no one actually understands how it works. Okay, right? No one has any theorem that says if you train, a neural net on all the text on the internet, then it will start, conversing intelligently. Okay, but just my friends or former friends at OpenAI just went and did that, and it worked. Okay, so maybe it'll be the same with quantum algorithms, right? We'll just throw them at these machine learning and optimization problems, and they'll give us this amazing performance. So there was a lot of discussion around something called the adiabatic algorithm, which is very much trying to do that. Here's the problem. The problem is, if you want to be honest in this field, you have to compare against the best heuristic algorithm running on a classical computer, right? Which could also work very quickly for reasons that no one understands, right? And and what matters is the differential between the two, right? So again and again, people will go to the press saying we use a quantum computer to do this neural net thing, to recognize handwriting, to route vehicles, and people will just say that's that's a huge achievement, right? And they don't even reach the point of asking, what to us would be the only relevant question, which is, are you beating the best classical heuristic, right? When you compare them head to head. And of course, the reason they don't ask is that the answer is no. Okay. But people have found examples. You can construct artificial examples, basically, where there seem to be very large quantum speedups, using these quantum annealing methods, for example. The thing we don't know is whether anything like those examples will ever show up in practice, right? So so I would say that the quantum speedups that we have for optimization and machine learning, they tend to be at least one of modest or highly specialized or speculative, right? So, and the challenge is to get one that is sort of broad and exponential, and we're confident that it's real. Okay. So there's been a lot of excitement also since the mid-2000s about a different class of quantum algorithms that sort of do linear algebra on exponentially large matrices and vectors and do it in polynomial time, right? So there was this famous HHL algorithm, it was called, after Harrow, Hasidim, and Lloyd, that seems to let you invert an n by n matrix in some sense in only log of n time. All right, so that sounds amazing. People got excited about that. The catch is, what it does is it maps a quantum state representing your input to a different quantum state representing your output. Okay, and now trouble is well, to actually be useful, first of all, you need a way to prepare the input state. Second of all, you need a way to measure the output state in a way where you would actually learn what you wanted to know, and there's not a fast classical algorithm that would tell you that same thing, right? So HHL kind of wipe their hands at that point. They say our job is done, right? You figure out what this is good for. Okay, but so often with these quantum machine learning speedups, the hard part is to find what we call an end-to-end speedup. right? It's very easy to get what looks like an exponential speed up when you're just talking about transforming quantum states. But at the end of the day, we want to start with a classical input and end with a classical answer and get from one to the other exponentially faster than we could do it classically. Okay, so here's a little case study just to show you the difficulty of this subject. So